In this tutorial, we will be looking at how to work out the frequency response of operational amplifiers, both on their own, so we'll be looking at their open loop gain versus frequency, and also when inserted in amplifier circuits such as the inverting and the non-inverting amplifier. Because the frequency response is something which is characteristic of real operational amplifiers, we won't be looking at all at the ideal amplifiers in this case, because ideal op-amps are meant to have infinite bandwidth, and hence it's pointless to look at those. The first thing we need to do, therefore, is import models for real op-amps. So we'll have to go onto Netlists, right-click, select Import Netlist, go onto the folder which contains your PSpice models, and we'll start with the 741. We'll click on the UA741, click on Open, and now this is imported in Microwave Office, and then we'll import another one by right-clicking on Netlist again, selecting Import Netlist, and then selecting the TL072, which is a higher performance op-amp. Now we've got them both in Microwave Office and we're able to use them. I'm not going to go through the stuff that I explained in tutorial 6 again, so I strongly recommend that you look at tutorial 6 before looking at this one, because otherwise you may get lost now and again. So first thing that we need to do, we need to go onto Circuit Schematics, create a new schematic. We'll call this Open Loop 741, and then we can simply place the 741 in the schematic by pressing Ctrl K and selecting the subcircuit UA741. Then we place this on the schematic. We can change the circuit symbol to make it more user-friendly. Right-click, go on to Properties, and then the Symbols tab, and scroll down until you get to the op-amp model. Click on OK, and there you have your familiar op-amp. Now we need to get ourselves some power supplies. Press Ctrl L and then DCVS, and place a couple of power supplies like so to give plus and minus 15 volts DC power supplies to the op-amp. Now that our op-amp is powered up, what we need to do is to provide an input signal, and we do that by pressing Ctrl L and typing in ACVS. This gives us an AC voltage source whose frequency we can sweep. Of course, we need a ground connection there, and then we'll connect it to the non-inverting terminal, and then we'll connect the inverting terminal to ground. And this way the voltage that ACVS produces will appear across our terminals. Now, an extremely important point to make is about the amplitude of our voltage source. We've seen in previous tutorials that we can only have very small differential voltages across our input terminals before we saturate the amplifier. So what we need to do is select the amplitude of this voltage source to be small enough so as to give us a meaningful output, not a saturated one. And one which is quite safe to use is 1 microvolt, since we saw that a few tens of microvolts was the maximum range that we could have. So if I double click on that and type in 1E-6, this gives me 1 microvolt in input, which is just what I need. Then at the output we need to have a load resistor. We'll make it as big as we want to avoid it affecting the response, but it's always good to have a load resistor at the output, even if we're looking at the open loop gain, because with real models sometimes you will have problems with convergence if you don't have that. So press Ctrl L, type in RES, place the resistor on the schematic like so, and then connect it to the output and to ground. Then give it a value of 100 kilo ohms. Now we need to have some measuring devices to be able to see the voltage at the input and the output. Press Ctrl L, type V_meter, and then place one at the input like so, and then press Ctrl C and Ctrl V and press one at the output like so. Now, of course, you must remember that the frequency of this element is set in the Project tab under Project Options, so we'll have to double click on that, and then what we can do is select the frequency range that we are interested in. So first of all, the data entry units, we will select Hertz, and then we'll start from 1 Hertz, and we will go up to 100 kilohertz, which is 100,000. Now the scale, of course we can choose a linear scale and a step, but this is a huge frequency range and we'd end up with tons of points. And as I mentioned to you before, it's very useful to use a logarithmic scale both in MATLAB and Microwave Office. So select the sweep type to be logarithmic, and then all you need to say is how many points you want per decade. You can select as many points as you like. I would advise to have 10 or 20 points. Let's try with 20 first, and then click on apply. And now you see the frequency range that has been created for you appears on the left hand side. Now let's go on to global units, and we'll change the frequency units to Hertz, and then click on OK. Now all we need to do is create a graph so that we can display the frequency response of the op-amp. So right click on graphs and select new graph and call it open loop gain 741. Then right click on the graph, select add a new measurement, and then we have to choose nonlinear as the measurement type and go on to voltage. And in this case, where MicroOffice allows us to directly measure the gain of a circuit, which is very useful. So we select V gain. Now, first of all, we'll have to choose the right data source name, and this is selected already. And then we'll have to specify which one is the input and which one is the output, so that MicroOffice can actually give us the gain. To do this, simply click on the three dots and the schematic appears, and we'll choose the input voltage as the one measured by the vmeter VM1, and then the output voltage as the one measured by vmeter VM2. Now, the harmonic index here is something that's important to point out. You remember in the first couple of lectures we talked about the distortion of the signal, and we talked about the fact that when we distort the signal, for example by hitting the rails, we end up creating harmonic components. So the signal is then split into more than one frequency component, and the main one will be the same one as the original signal, and we will have extra one created at multiples of the frequency of the original signal. MicroOffice allows you to measure this kind of distortion by looking at the harmonic components of the signal. But in our case, we will simply choose the harmonic component 1, which is the frequency of the fundamental signal, and we would ignore any harmonic components that are generated. So this is a very useful thing, but you have to be careful, because if your signal is nonlinear and you get distortion, then by doing the measurement this way, you will lose information about the power that goes into the harmonics. Then you of course have to select magnitude here and then dB, and then click on apply and OK. And now simulate. You can see that thanks to the fact that we've selected a logarithmic scale, the simulation was extremely fast, although we looked at frequencies between 1 and 100,000 Hertz. Now you may see that this graph is looking a little bit weird, and the reason for that is that we haven't changed the scale to logarithmic on the x-axis. Although we set up a logarithmic set of frequencies, MicroOffice doesn't automatically change the scale to logarithmic in the graph. So to do that, right click on the graph, go on to properties, and then on the axis tab, simply tick log scale. Then click on apply and OK. And now you see that the frequency response is what you are used to seeing. You may see that with the frequency range that we've selected, we haven't actually hit the 0 point, which will give us the bandwidth of the amplifier. So what we can do is go back to project options, and then go to the frequencies tab and simply increase the frequency up to which we're simulating. So let's simply add an extra 0 here, which will take us to 1 MHz. Click on apply and then OK, and then simulate. You can see that this time we are indeed hitting the 0 point. Now an interesting thing to do is to have a look at how the other amplifier behaves, and to do this we can simply create a new schematic and use the op-amp TL072 instead. To do this, what we can do is simply duplicate our schematic. We don't have to put everything back on. And to duplicate a schematic, you either right click on it and select duplicate schematic, or you simply click on the schematic and drag it onto the circuit schematic heading, and this creates a copy. Then you right click on it, you rename it, and we'll call it open loop TL072. And then in our schematic, all we need to do is simply change the network name that this element is associated to the TL072. It's as simple as that. So this way we'll change the op-amp from whatever it was before, which was MUA741, to TL072. Now we can go back to our graph and we right click and select add a new measurement. The measurement will be pretty much identical apart from the fact that it comes from a different schematic. So we'll select it right here and then we'll just check that the settings are correct. The voltage in component is correct and the voltage out component is also correct. And of course the harmonic index is 1 because we're just looking at the fundamental frequency, we're not looking at any harmonics, assuming that we don't have any distortion. Click on apply and then OK, then simulate. Now let's make this legend a little bit smaller and you can see that the frequency response of this amplifier is actually better than the 741. It seems to have a wider bandwidth, but again we can't see the 0 point. So a good thing that we can do is go back to the project options yet again and increase our frequency range further. So let's increase it to 10 MHz and then click on apply and then OK. Then simulate. Now you can see the frequency response of these two amplifiers and you can see that the bandwidth, which is the frequency range over which the open loop gain is greater than 1 or greater than 0 dB, is larger for the TL072 than it is for the 741. We can put markers in by right-clicking and selecting Add a Marker and then clicking on the curve, and we can do the same for the TL072. You can see that the bandwidth for these two differs by quite a bit. The bandwidth for the TL072 is about 3.4 MHz, whereas for the 741 it's just under 1 MHz. So let's now move on to look at the frequency response of amplifier circuits and see how they compare with the open loop response. So let's simply go on to Circuit Schematics and select New Schematic. We'll call it Inverting 741. Now we don't want to put in the same elements as we did before yet again, so we can simply go to the previous schematic Open Loop 741 and then select a bunch of stuff and copy it into the new schematic, and this will make our life a lot easier. So I can simply select by clicking and dragging this whole bit here and then pressing Ctrl+C and then clicking on the schematic that I've just created and then pressing Ctrl+V, and here we go. I've got all my stuff copied in with all the power supplies, which makes life a lot easier. So let's first put together an inverting amplifier. So let's remove this ground here and we simply put a ground on the non-inverting terminal. And then what we'll do is get a couple of resistors, Ctrl+L plus RES. Let's give the resistors appropriate names. We'll call this RL, and then we'll call this R1, and we'll call this R2. And then we'll give it a gain of 10 just to make life easy for us. And we'll do this with kilo ohm resistors. So we'll do 1 kilo ohm here, and we'll do 10 kilo ohms here. And what we need to do, of course, is have a voltage source. Press Ctrl+L and ACVS, and then we'll put a voltage source right here, and we connect it to this resistor, and then put a ground connection down here. Again, we have to be very careful with what voltage level we put in here. In this case, we can go a lot higher, but bear in mind we have a gain of 10. So if we have a voltage of 1 volt here and an amplification of 10, then we'll have a 10 volts peak voltage at the output. Personally, I'd quite like to take this down a little bit, and I'll use an amplitude of 0.1 volts instead. And the reason for this is that if your input voltage is quite high, then the output voltage is also quite high, and you might end up having problems with the slew rate. So when you're doing a frequency response, try to keep the voltages small, so then all you see is the effect of the frequency response of the amplifier, which is linear, and you don't incur in any of the nonlinear problems that a slew rate would bring about. So now yet again we need some voltage meters. Press Ctrl+L and then again go for V_meter, and let's place one at the input, and then press Ctrl+C, Ctrl+V and place one at the output. Now we're all set and ready to go. We've already defined the frequency range for this particular SIGGEN, so we won't be changing that. We'll keep it just the same. Now we can go on to graphs, and we can actually do the same as we did with the schematic. We can simply duplicate it. So we can right click on it and select duplicate graph, or we simply click on it and then drag it onto the graphs heading, and we get a second graph. We'll rename it and we'll call it open loop versus closed loop 741. Now we've got two measurements here. One I want to keep, and that is the open loop gain of the 741. But the other one I just want to delete. So I'll just click on the one for the TL072 and press delete. Now I can right click on the graph, go on to add a new measurement, and then I'll pick the right schematic, which is inverting 741. And then I'll just go and have a look and see that I've got the right gain measurement components. And indeed, we've got the right voltage meter in the input. We have the right voltage meter at the output. And of course, we have the harmonic index set to 1, which is what we want. Magnitude is in dB, perfect. So click on apply and then OK. Remove the marker and simulate. You can see that the frequency response of the op-amp in an inverting configuration has decreased the gain considerably, but it's also make it flatter across a much wider frequency range. And then we see that as we hit the corner frequency for the inverting amplifier, we start going down at the same rate as the open loop gain, but the two curves don't entirely overlap. And we saw this in the lectures. There is a little bit of a gap between the curve for the closed loop gain of an inverting amplifier and the open loop gain of the operational amplifier on which it is based. We can add an additional schematic now and look at the gain for a non-inverting amplifier. As we did before, we can simply click on the schematic and then drag it onto the heading, or simply right click on it and select duplicate schematic. And then we'll have to rename it to avoid confusion, and we'll call this non-inverting 741. And now, of course, we have to juggle things around a little bit to make sure that we've got the right configuration. So first of all, the input signal should not be here. Then I have to get rid of all of this and place a ground at this side of this resistor. And lo and behold, we've already got ourselves a non-inverting amplifier. The thing is, however, I want this non-inverting amplifier to have exactly the same gain as the inverting one. And at the moment, this has got a gain which is higher by 1. And that is because the gain of a non-inverting amplifier is 1 plus R2 over R1. So to make this gain 10 as well, I need to make this 9K. And then the gain would be 1 plus R2 over R1, which is 9. 1 plus 9 equals 10. Now I can go back to the graph of open loop versus closed loop gains, right click, and then select add a new measurement. And again, this would be V gain, but this time I'll pick the non-inverting 741 schematic. And we need to go in and make sure that we do the measurement the right way. We can directly pick this element to have the input voltage. We don't necessarily need a voltage meter. I've been putting that in to make sure you do things right, but you can simply have this selected and it'll be fine. And the measurement component of the output would be VM2, which is correct. Click on apply and then OK, and then hit simulate. Now you can see that this is remarkably similar, almost entirely overlapping the curve for the inverting amplifier. Of course, we can repeat this for the TL072. This is not something that I'm going to show in the video because by now you should be able to do this on your own. I hope that this video has been helpful, and it will certainly be very helpful for you to be able to do this kind of stuff before our first lab in week 20.